Should I start talking?
Yes, you're ready. Yeah, you're ready.
Oh, okay. All right. Thanks, everyone. I can kind of see you and kind of hear you. If you have questions, this could be a bit tricky. You may have to gesticulate a lot, stand up, and maybe yell. Okay. The other thing is, I'm just going to assume you can hear me okay. I can't control the levels in the room. The other thing is, unfortunately, Chaba didn't give me much warning. I simply don't have time to prepare slides or anything, so I apologize. So what we get is some multimedia experience where I'm going to swap between, document outlines, going through the actual paper and showing a couple of demos in like a Julia simulation. Hopefully this is coherent. It probably wouldn't be much better in person anyway, because I'd be probably in the same setup. But here goes. If things are unclear, please speak up. So the mandate that I was given, as I understand it, was to talk about this paper, which I should maybe pull up here, which is about the Turing completeness or the computational universality of large language models. And so what I plan for this lecture is to actually essentially walk through the content of this paper and then maybe at the end share some more recent results. But just kind of show you the nuts and bolts of how this, basically this proof and this construction works. Now, it sounds like, okay, I don't want to contradict myself. It might sound pretty trivial to prove that a language model is a universal computer or Turing complete. I've heard many dismissive comments over the years, and yet this is my best shot. This is the simplest proof I've been able to construct, and it's about 40 pages. But it's not complex. It's actually a very straightforward proof construction. But, this is a chance to see if other humans can actually follow the construction and see if you agree. All right, so assuming you can see this doc, I don't know if the display is big enough for you to be able to read anything, to be honest. Can somebody, is there like a way to give me a thumbs up or thumbs down? Can anyone read this outline? I have this document here. Is it readable at all?
You can zoom in.
Let's see here. This Zoom button would do the trick. Is that better?
Yeah. Yes.
Okay, well, we're going to have an issue with this, so I need to zoom this in as well. Okay. All right, well, anyway, I'll come back to that one. Okay, assuming, sorry about the infinite mirror thing. I've just got to keep swapping between windows. Okay, so assuming you understood the intro, here is the plan, okay? And we started late, so I'm going to rush. Hopefully I can at least get parts of this across coherently. I'm going to just start with a brief intro, kind of set things up. And then I'm just going to kind of go through basically the sections of this paper, but sort of step by step showing how this argument is built up. After an intro, just quickly review autoregressive decoding and some of the modifications we have to do there. Introduce this concept of a leg system, which was actually invented around the dawn of thinking about computers. So this was invented in the 1940s. It turns out leg systems are probably the closest known formal system to language models, and we will definitely use that in our proof. Next section will be to basically dive into leg systems and show how they create memory queues and how we can use a leg system to control position, to sort of execute position control in a memory queue. This will wind up being critical. Once we know how to do that, basically we're home free. Sort of quickly review Turing machines, which do bidirectional access to a memory. And then essentially we just show that you can simulate bidirectional access to a memory with just simple queue rotations. Section 6 is the actual proof that a universal leg system can be constructed to exactly simulate a universal Turing machine. And then section 7 sort of concludes the proof by showing that a language model can simulate the universal leg system, which can simulate the universal Turing machine. finally, okay, that's what Section 8 does. And then finally, I'll talk about some of Alex Lewandowski's recent findings about proving random machines are universal. Anyway, see how this goes. I can only partly see or hear you, so please do interrupt if I'm not clear. Okay, so the first thing I need to do is set up, a language model, autoregressive generation, and then, what a universal computer is, and sort of, just remind you about the Church-Turing thesis. So to do that, let me pull up this paper. Maybe shrink this a bit. Okay. I assume you're all familiar with the chain law of probability, but forgive me, I have to remind you of the chain law. So in a language model, right, what we have is a conditional probability distribution over a finite set of symbols, right? So here, I'm going to use, letters S to denote individual symbols or tokens, if you will, in a sequence. So a large language model is just simply a conditional distribution over the next token, say here S1, given some context, which here is written Sn plus 1 to Sn plus n. Anyway, and we know that if the ability to generate a single next token here can simply be chained to generate a sequence of next tokens, and through the chain law of probability, or the chain rule of probability, we know that the probability of a sequence given a context can just be decomposed into this product of probabilities of each individual symbol given this context. So we can exactly write the probability mass of the sequence in this decomposition. But we can also leverage this decomposition to sample the sequence by successively sampling each next token and then adding it to the previous context to sample. So what's called autoregressive decoding is really just a sampled version of the chain rule of probability. Okay. So basically that's what a language model gives us, a particular conditional distribution. Sorry, I have to quit doing that. A particular conditional distribution over next token, given a context. And the question we face is, if you gave me a particular conditional distribution model like this, can I use it to emulate a general purpose computer? Okay. Now, I guess I would have talked about this in some previous talks. I don't have the slides here right now. But the main challenge is that the language models as we currently understand them, they're based on transformer architectures. And a transformer architecture, maybe if you looked at this figure 1 here, a transformer architecture is only ever going to have a context window up to some bounded size. So this would define, if we're doing autoregressive decoding, this would define essentially a K Markov model. So a model, so you could see here in this equation too, a model where the probability of a next token, given a long sequence where that sequence length is longer than the context window, that would be, by a K Markov assumption, be determined solely by looking at the most recent K symbols. So if we're looking at a transformer architecture, we are essentially looking at a K Markov model. And a K Markov model is essentially a stochastic finite state machine. And a finite state machine, if you remember your sort of basics of computability theory, a finite state machine can only ever recognize regular languages. So it's provably restricted. It cannot be a Turing complete system. Okay. So the first challenge we're going to face is we have to understand how we can essentially take a stochastic finite state machine by the language and somehow deploy that in a natural way to simulate arbitrary computation. And the key is going to come down to memory. We're going to have to somehow operate on large inputs that are larger than the context window. And we're also going to have to operate on long computational sequences that are larger than the context window. If you operate solely within a bounded context window, it is not possible to be a universal computer. Okay, so step 1 is we have to sort of figure out some way to get a K Markov model to operate on an input string or a memory string that's much larger than k, all right? And so here's sort of the first sort of technicality that we had to address here, is to extend this kind of chain rule of probability to this thing that we'll call extended autoregressive decoding. And it's a very trivial looking extension. It's very minor, but it winds up being critical. So let me go back to these diagrams here. So if you look at this figure 1, these two, these sequence here at the top, what you will see is basically how a K Markov model can operate over a large input string. So imagine I give you a large, so say your context window is size K, and I give you a context string that's bigger than K, say length N or something, and then you generate, say, a next token. How are we going to, operate, run our K Markov model over an input string that is larger than the context window while still remembering the tokens that the model generates? So our first step is to extend autoregressive decoding to simply recognize that standard autoregressive decoding is a generate and append structure. So in standard autoregressive decoding, given the context, you generate the next symbol, you append it, and you grow the context. Okay, and then now you feed in the larger context, generate the next symbol, append it, and grow the context. So the first step, what we call generalized autoregressive decoding, is simply generalizing this append operation to the end of a working string that is bigger than the K context window, size K context window. So this essentially is it's a trivial generalization of autoregressive decoding to operating on strings that are bigger than the context window. Okay, now that's nearly enough. So it turns out if you just allow this simple extension, we're going to ultimately see this is enough to implement a linear bounded automaton. And linear bounded automaton are powerful enough to recognize context sensitive languages. Context sensitive languages are more general than context free, which are more general than regular languages. So this is far beyond what you can do with a finite state machine or a K Markov model. So even though this looks like a trivial extension, this generalization allows a K Markov model to operate over a larger memory than size K, and this is a very powerful extension. We will see later that this will give us the power to recognize context-sensitive languages. Now, context-sensitive languages in the Chomsky hierarchy are a very general class, but they're one step below Turing complete or recursively enumerable languages. Turns out there are languages in the gap, so this is not sufficient to implement or realize truly universal or general purpose computation. So we will need one further extension to the autoregressive decoding structure. And it's a very trivial looking extension, but it is simply taking this, this append operator where I take a context and I generate one symbol and append it. I just simply have to extend that to sometimes allow the model to generate two symbols instead of one. Simply allowing the model to generate two symbols instead of one, turns out that is going to bridge the gap from context sensitive to general Turing complete languages. Now that'll sound pretty obscure, it's a very trivial extension, but we will use this later on in the proof. Okay, now this probably seems mystical, but the other thing that's, okay, actually, let me show you one more thing, and then this will all become clear why we need to do these things. So okay, I have to skip ahead a bit here. Just want to show you one figure. Okay, one thing about this generate and append, okay? If I give you a generate and append mechanism, right, where you have, say you operate on a context window, like in this line 4, you operate on a context window of size n. We're given a context of length n. You generate a new symbol, but then you then you add it, you append it, and now you have a sequence of length n plus 1. But let's say n was the size of your transformer context window, then we would have to delete the first symbol. So when we're operating, say, at a memory buffer size of n, when we generate and append one symbol, we would lose the first symbol. Now, if we do this, it turns out if you just simply append the first symbol before you delete it, what you can see immediately is that you would create a circular queue. So a K-Markov model can actually implement a circular queue over memory, all right? What's even more useful is that a K-Markov model can generate a circular queue of period bigger than K. So if we combine this idea of a circular queue where you're at the buffer size, you append a symbol and you have to dequeue the first symbol. If we combine that with the K-Markov assumption, it's going to turn out, right, that we can create a controller, a K-Markov controller that can operate over a memory string where we can have full access over the memory string by basically rotating the memory string, okay? So this is kind of like one step. This will get us up to context sensitive. And then the only thing remaining is that if you can get sort of arbitrary memory control read-write access over a bounded size memory, the only other thing we need to achieve to get all the way up to Turing completeness is we will need the ability on an instance by instance basis to grow memory as needed. So a Turing machine, there's two ways to look at it. You've probably been taught about a Turing machine as either having access to accountably infinitely large memory, but equivalently, you could look at a Turing machine as being defined over a finite memory, but the machine is allowed to grow the memory as it computes. So what we'll find is that if we allow the system to grow the memory as it computes, that will bridge the gap from context sensitive to Turing complete, and we'll be able to show that we can simulate arbitrary Turing machines. Okay, so there is a question. So I need to avoid the Hall of Infinite Mirror thing here, so I won't see you, but I can hear you.
Oh, no, I mean, I could unmute, but you can ask. Can you hear me?
Barely.
Okay. Can you explain? Where's the mic? Up here?
I can
hear me now.
Yeah.
Okay. Can you explain again, like, in the circular queue thing, you, for instance, had like some symbol x1, and then you didn't append it, then how would you ever retrieve it later on? Like, I don't understand how the memory can be simulated to like be infinite memory.
You mean this thing here, S1 to Sn?
So that makes sense, but then
yeah.
How do you keep things in memory that's bigger than the size n?
Yeah, like if n is the size of the transformer context. Or
yeah, how do you keep anything bigger than that?
Yes, so clearly what we're doing is we're basically storing a memory string outside of the language model. So, and I will argue this is a necessity. So it looks like Vlad, by the way. It's a very tiny Vlad, but I think that's Vlad.
Yeah.
Nice. Just a reminder that when we're talking about like general models of computation, like say, like in the Chomsky hierarchy or things like that, when we talk about a language, which is a set of strings, we generally will talk about languages that are infinitely large. That is, a language that contains an infinite number of strings. And we need to do this, okay? Why do we need to do this? If you give me a bounded size, like an upper bound on the length of the strings that I'm going to compute over, then for any bounded sized family of strings, that family of strings must be finite. So by a string by definition, right, is a finite length sequence of symbols from a finite alphabet. So if you put an upper bound on the size of the string, you have completely constrained the size of the set of strings to be a finite set. And now if you never leave that finite set, you will be a finite state machine. And so all models of computation beyond finite state machines cannot be restricted to operating on strings of bounded size. So if we're going to talk about models of computation beyond finite state computation, we must consider how do you compute on strings that are bigger than any bounded size, strings that are unboundedly large, okay? Or put a different way, any infinite set of strings cannot have an upper bound on the size of any individual string. Any infinite set of strings must have strings of arbitrary length in it. And so if we're going to compute, like do language recognition or compute on sets of strings, where the set of strings we can operate on is an infinite set, then we must consider how do we compute on an arbitrarily large strings. So that's kind of the key thing we have to face right up front.
Yeah, I agree.
Okay, so the way we're going to do it is we're going to keep the string memory separate from the language model. So the language model is going to have its context window. It'll have a view of that string, but it will never see the whole string.
So if it does, okay, that's fine.
Okay. Sorry, wow, this is coming across way more technical than I really wanted it to be. But anyway, I'm sorry. I don't know if a whiteboard makes it better. Okay, so, all right. So back to the agenda. So, okay, here's what I'm going to do, right? What I'm going to do is temporarily, I'm actually going to step away from language models, and I'm going to introduce this new formal system called a leg system. Well, it's not a new formal system. Leg systems were invented by Emil Post. I don't know if you've ever heard of Post systems or Emil Post, but he was a logician who was active at the same time as Gödel and Turing and Church. And around the church, the rise of the Church Turing thesis, this unification of general models of computation, at that time, Post also invented different models of computation that were later proved to be equivalent. Okay, and a leg system is a model of computation that was invented by Post in the 1940s. And the theory of this system was developed in the 1960s. And it turns out once I show you how these systems are defined and how they work, you will recognize that these are the natural systems that actually describe how language models basically compute. Okay, so I need to take a side journey into introducing you into this formal system called a leg system, how it computes and what we can prove about it. But then I need to show you why a leg system is a universal machine. And the way I'm going to show you that why a leg system is universal is I'm going to show you how you can use a leg system to simulate an arbitrary Turing machine. So that's kind of most of the work, actually. So let me back up here, see if I can explain a leg system to you. Actually, it's probably easier first to start with. So let me show you an example. Okay, so a leg system is a very simple idea. So it's just a pattern matching system. So a leg system, we're going to have a working string. So if you look down here, I have this abba, kaba, baba string. Sorry, it's just some nonsense. I have a string. We're going to call that like the working, it's basically the working memory. So a string, okay? And a reminder, a string will be, a sequence of symbols where the symbols come from some finite alphabet. Here, the alphabet would be ABC, okay? So a leg system is defined by a set of pattern matching rules. So above here, you can see this is a set of pattern matching rules. Now, each rule, is going to have a left-hand side and a right-hand side. And the way the system works is it's very simple. The right-hand side is just going to be a pattern, but it's going to be a trivial pattern. It doesn't have any fancy symbols or anything. It's literally going to be a string. So here, the first rule is a string AB, right? And then the right-hand side is going to be mapped to a string, but here the string is a length 1 string C. Okay, so we have strings on the left-hand side of these rules and strings on the right-hand side of the rules. Now, the operation of this system is trivial. So any leg system is defined by a finite set of rules on some finite vocabulary. And it will compute on any input string chosen from that same vocabulary. Okay. So we take this input string, and then we will match on the leftmost end. So we take the start and we find, is there a rule that matches? Now, you could see that I could actually write an ambiguous rule system. So this happens to be an unambiguous rule system. There's only, for any pattern match, there's only a single rule. So this will be a deterministic system. You could create non-deterministic systems by having multiple, copies of the same pattern. Okay, but let's stick to deterministic systems. It's all we're going to need. So, here, because the patterns on the right are uniquely occurring, it's a deterministic system. I look at the first two symbols in the string. I see a match to the first two symbols here. So I apply this first rule. Now, the update is simple, but it's a bit, I have to explain it. Now, the update is that you take the symbol on the right and you append it to the right, just like a language model. You'll generate a symbol that you append to the end of the working string, okay? But then you delete the first symbol. So essentially, you could think of a leg system as operating on a string, but that string is literally a queue. Every compute cycle, you enqueue, you append a couple of symbols, and you dequeue one symbol. Okay, a general leg system, you're allowed to dequeue some fixed constant number of symbols, but we're going to operate in queue systems where we, in every compute cycle, dequeue one symbol. So this is like a one leg system. Okay, so you match the left-hand side, you append something to the right, and you drop one symbol. Okay. So now this goes back to this sequential queue thing I showed you earlier. If all my pattern match rules are of the same length, and we dequeue one symbol on each cycle, and we enqueue one symbol on each cycle, then the size of the memory string will stay constant forever. It doesn't have to implement a queue, it doesn't have to implement a cycle. As you can see, we can have all kinds of interesting behaviors. But if we always just, if the right-hand side is always a single system, then we will keep the same size of memory forever. Okay. To have interesting behavior, we will need at least one rule to append two symbols. And if you have at least one rule that appends at least two symbols, then in principle, it's possible that the computation can grow memory as it goes. And the other thing is that in principle, if the computation can grow memory as it goes, you can get non-halting computations, right? You can actually grow memory endlessly and not halt. Now, how these systems halt is one halting condition is that you could wind up with a string where the left-hand side doesn't match any rule. If there's no matching rule, that's a fail. It's basically a halt and reject. Okay. Now, you could also do this with a special symbol. You could introduce a special symbol, like we could say C is a special symbol, and you could halt whenever you generate C, or you could halt whenever C winds up on the left hand of a rule. So we're generally going to set up leg systems where we're going to have an explicit halting symbol. And we can do it with an explicit halt and accept or an explicit halt and reject. Okay. So the first thing we need to understand is how powerful are leg systems. So here I just have a trivial example of how a leg system computes, match the left-hand side, append the symbol, delete the symbol on the left, right? So NQ and DQ in each cycle, okay? Now, I'll cut to the chase. It turns out with a finite set of rules in a leg system where I have at least some rules that append two symbols, and all the other rules append one symbol, you can simulate a universal Turing machine. And so the next step is I have to show you that just by using this kind of system, I can simulate a Turing machine that has arbitrary memory access operating on that memory. Okay. Now, most of that is just kind of a little bit of detail, but I think there's a couple of intuitive demonstrations I can show you that makes it clear why you can do this. Okay. Now, it's actually initially not completely obvious that you can simulate a Turing machine using a queue system. Why? Because in a Turing machine, right, a Turing machine like a leg system, you could look at the memory of the Turing machine as a finite length string, okay? But in the Turing machine, you have a separate finite state controller. You have a read-write head looking at some particular position in the string, okay? And you can write at that position and you can move bidirectionally. So a Turing machine is going to move back and forth over the string, following some finite state control rules. And I'll give you a couple of brief demos shortly, okay? And the question is, okay, unlike a bidirectional moving Turing machine head, a leg system has to operate memory as a queue. That is, we can, by dequeuing the symbol at the start and enqueuing it at the end, we can rotate the memory, even if the memory is bigger than the context window size. So for example, we could write a rule system here that can, has, say, a context window size of 2 that can rotate memory strings of arbitrary size. But, and such, actually, I'll do it live. The simple way to do it is you just, actually, I can do it with a leg system of size 1. You just literally copy the symbol to the left and right? So if I DQ and NQ the same symbol, then what you will see, so this is a leg system with window size 1, okay? If you apply this leg system of window size 1, say for example, you're going to see that you DQ the A, but then you NQ the other end, right? And then you DQ, and then you NQ the B at the other end. So what did we have? Like BA, A, B. And if you continue this, you notice that you would take the original string and you would literally rotate the whole string. Okay? So with a leg system, you can basically have a queue machine. The challenge is the queue machine has no external controller. The only control it has is pattern matching, like NQ and DQ according to pattern matches. There isn't like a finite state machine. And the other thing is the queue machine can only operate in one direction. So it can only progress in one direction through memory. It cannot back up. Okay. So to simulate a Turing machine, we have to figure out a way to do two things. We have to be able to keep track of the state of the Turing machine, and we have to be able to operate on the memory and moving the position where we're operating in memory in both directions. Okay, so frankly, the longest part of the paper and the most detailed, but actually simplest part of the proof is just simply demonstrating how by using queues implemented by a leg system, you can both keep track of the state of a Turing machine, but even more importantly, you can keep track of a position, a read-write head, and you can move the read-write head in both directions. Okay.
There's a question.
Oh, sorry, question. Yeah.
This lag system is something like, still like a K-Markov chain, right?
It's, yeah, here is like one, so one Markov is enough to rotate memory.
Yeah, I'm a little confused about the first thing that you said, that when we have a K-Markov chain, it's still finite and it cannot turn into a universal Turing machine, right?
Yeah.
How we can escape from that?
Sorry, say again?
I mean, how we can escape from that condition here? The lag system is still a special case of K-Markov chain.
Yeah, so, okay, A, B, C. Okay, so let's do our rotation, right? So it's going to go to B, C, A, right? And then it's going to go to C, A, B. And then, by the way, this system will run forever, right? It's just going to go A, B, C, right? And then ... Okay, so here's an example of a one Markov model that is operating on a string of length 3. So obviously the string, the memory string, is bigger than the context. Okay, so I'm sure you got this, but just to be clear, right? So then we have this leg system that it shows you that it can basically just rotate that memory string. But rotating the memory string will never grow the memory string. And if you can never grow the memory string, there's no way you can operate like a universal Turing machine, because a universal Turing machine, in principle, can operate over larger and larger and larger extents of memory as it computes on a single problem instance. So it's actually really straightforward to show that you can grow memory by just taking one of these rules and having it, like, say, append 2 symbols instead of 1. Right? So if we just have a single rule that appends more than 1 symbol, say 2 symbols, then you could see here that what we would get is this setting, where we would start with a string of length 3, but then after a few steps, we wind up with a string of length 4. And if we continued running this, it would basically, as you could already see, it would grow a string of A, B, and then C, 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 C forever, right? It would just get longer and longer and longer. So every time you rotate, you make a lap around the string, you would append another C. So that's how this system can expand memory, just by having a generator that appends more than 1 symbol.
Right, thank you.
Yeah? Okay.
Yes.
Okay, and we have to use this if we're going to have a universal Turing machine simulation. We're going to need to grow.
We have another question.
Yeah.
Yeah, I was wondering, similar to Vlad, I'm still confused how a language model can simulate a queue bigger than its context window, which I think is like central for simulating this lag machine
Yeah.
or this lag system.
It's going to operate exactly like this. So you're, by the way, the proof is not impressive. I'm just saying it's a proof. I'm not saying it's, the proof at the end of the day is literally going to be getting the language model to simulate exactly one of these leg systems. And so the language model is literally going to be looking at, there's going to be a big system prompt, but it's literally going to be looking at a small context window. And then we're just forcing the model to generate the correct response in each of the possible contexts. And so that small context window is going to compute over input strings that are really large. I have some by the way, I've coded all this up. I'll show you a couple of demos. But you can see that the leg system at least will grow the memory. And then we just simply showed that we could prompt a language model to exactly simulate the leg system. Okay, maybe what's confusing to you is that the language model, so like a leg system, the working string, the memory string, is outside of the language model. So we basically would construct, so we'll have a working string. The language model can't see the full string. It's huge, right? So there's an external thing which just cuts off a piece of the string, hands that as a context to the language model, gets the language model response, appends the language model response, and then shows it the next piece. Maybe that's what you're missing.
Yeah, that makes sense. Thank you.
Okay. Okay. Let's see here. So, yeah, I'm sorry. This probably feels very obscure. I apologize. And again, I have no time to make slides, and that's life. Okay. So I'm going to, let me show you. So I'm just going to show you a couple simple constructions of how we can use this lag system, this append operation, to implement position control. And I'm going to do this so there's just two directions, right? So we just need to have a marker on our memory string that shows where our current read-write head is. And then we need to be able to move the marker like one step to the right and one step to the left, okay? Now, in this system, the memory is actually going to be a circular queue. So when I say one step to the right, I kind of mean one step clockwise. And when I say, say one step left, I mean one step counterclockwise, okay? Now, so this picture, I don't know if you can see this picture here I've highlighted. Sorry, this equation 5 thing. This depicts a rule system where I'm going to use a position control marker P, okay? And I'm going to have a big string, but the string is always going to be expressed as pairs. So I'm going to have like okay, actually, let me show you a different document. Okay, so the way I'm going to simulate Turing machines with a lag system is I'm going to construct, you give me the Turing machine, I'm going to construct the symbols that make up the strings for the lag system. But when I construct the symbols for the lag system, they're not going to be in a one-to-one correspondence with the symbols of the Turing machine. What I'm going to do is I'm going to create new symbols for the lag system, okay? And the new symbols, I'm just going to, like it's syntactic sugar, the new symbols are going to be tuples, okay? So I'm going to create a new symbol that is like a list of symbols. Do you understand? So for example, later on when we simulate a Turing machine, one symbol for the lag system is going to be a triple. It's going to be a triple of 3 symbols, where the first symbol is the data symbol for the Turing machine, like the symbols that occur in the Turing machine memory. The second symbol is a different symbol that's going to be the state of the Turing machine, or a blank. Okay. And the third symbol is going to be a symbol I'm going to call a position control symbol. So the lag system is going to operate over tuples. Okay. What's the only thing that's important though is that there's a finite set of tuples. So if there's a finite set of tuples, then I'm going to declare that's a finite vocabulary upon which we can define strings and upon which we can define leg system rules. Okay. So in the first step of the construction here, I'm going to simplify it because we're not up to Turing machines yet. I'm going to define symbols as pairs. So I'm going to take whatever base alphabet you have, like you have some strings and some alphabet, but I'm basically going to augment each alphabet symbol with a position control symbol. And I'm just going to, I'm basically going to hide or tag it with a position control symbol. And the position control symbol here is going to be either blank or P, okay? And I'm going to set it up so that in every string, there's going to be a single position that is marked with P, and every other position is marked blank, okay? So for example, here, this kind of string here, we have a string of pairs, and every pair consists, it's a pair where the first symbol is from some other alphabet, like our data, and the second position is just going to be position control, which is blank, 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 blank everywhere, except we put a position control on like position n-1. Okay. And what I just want to show you is how a leg system works. This system of rules up here, these three rule patterns, which basically expands into a finite set of rules. This leg system defined by this set of rules basically will preserve the data string, but what it will do as it operates is it will move the position control symbol one step to the right, one step to the right forever. So it's basically going to move the position control symbol clockwise around the data string. And we need this capability to kind of keep track of a Turing machine read-write head position. And so this will keep track of the position and also move it clockwise around the data string. Okay. So we have less than an hour, so maybe I'll drop into demos. Let's see here. Can you guys sort of see what's in this window? Is this big enough to see? There's not much going on. Sorry?
Maybe a little bit bigger.
Still bigger? Okay. Is that big enough to see?
Yes, thanks.
Okay. By the way, just skipping ahead, this is a depiction of a trace of a Turing machine. Okay, so I haven't shown you the Turing machine, but here's an input string to the Turing machine. So we're going to assume one-sided memory. So there's a leftmost position, and then you'll notice at the right I have a special delimiter symbol. Okay, so this just shows a simulation of a particular Turing machine operating on this input string. And so you can see in the way that simulation works, this position that has an underlined red, that's just the position of the read-write symbol, okay? And then this letter A is the state of the Turing machine. So this will just show like we start a Turing machine, it's in state A, the full input string, 1111, 0000, and then the read-write head is in position 1. And then it turns out if you're in state A and you read a 1, you move one step to the right and you keep the 1, right? And so you can just see each step of the Turing machine as it operates on this string. And it, notice that here it just keeps preserving, just keeps overwriting the same symbol until it gets to this position here, and then it changes state to B, and then overwrites a 0 with a 1. Anyway, this does something, okay? All right, now I want to show you a couple of leg system demos, and then I'll give you back to some Turing machine simulations. So, hang on, I need my little guide here. Okay, my first leg system, just make sure I'm in the right place. Compilers, nope. Space machine. Oh, by the way, I've implemented, Turing machines and leg systems and all kinds of other systems and built compilers that translate between them. And essentially, the proof is a compilation of a Turing machine into a leg system. But anyway, okay, so let me show you one of these. Sorry, I implemented everything, Julia. I apologize. Are we looking for TM? Oh, okay, that's the Turing machine. Come on, Julia. Here we go. Okay. All right. So this, let me just show you something. So this is going to be a running example that I can use to show this, although time is burning. Okay, this is a Turing machine that recognizes strings of zeros and twos, 0, 1s, and 2s, where it will accept a string where you have the same number of zeros followed by the same number of 1s followed by the same number of 2s. Or put another way, it recognizes the language, 0 to the K, 1 to the K, 2 to the K. All right. And you can see it's scanning back and forth across the string as it computes, and it's basically marking off, right? So it marks off a 0, and then it's trying to see if it can find a 1 next to mark off, and then it'll try to mark off a 2, and it'll keep going back and forth, marking off a single 0, a single 1, a single 2, until it decides it's marked everybody and there's nobody left. Then it'll accept. Okay, but if you sneak in an extra 0, when it goes around marking things off, it's going to detect there's an extra 0 and it'll reject. Or if you sneak in an extra 1 or you sneak in an extra 2, it rejects. Okay. All right. So that's just some Turing machine that we will be able to simulate. Okay, but let me. Okay, I might have to exit here. So let me show you a leg system showing this. Sorry, SLAG is strict leg system. Sorry about that. Example. It's going to run everything, but I can walk you through what it's doing. All right. So this is an implementation of the system I just showed you. So this system right here in equation 5, it's got these 3 rule patterns. It basically says if you see blank blank, that means there's no position control. You just append the first symbol. It's just rotating the cube. So when you see blanks, you just move the memory. You rotate memory. Okay. But then it does this funky thing when you see a blank P, it's going to generate a P. And what this is going to wind up doing is it's going to shift the position control symbol, 1 step to the left. And then this P blank is going to delete the old position control symbol. So the operation of the system might seem a bit obscure, but this demonstration shows you exactly how that symbol system works. Okay. So here, here's an example of a string where there's 6 data items, right? So the data is just called 1, 2, 3, 4, 5, 6. Okay. But then the leg system is looking at pairs where we have a data number, and then we have a position control. And the position control is blank or P. And we initialize the memory in the 5th position with P. So basically we have a position control marker in position 5. Okay. If you run this rule, so what the simulation will show is that if you run this rule system, you'll see this unique, right? So that the pair of blanks 2 and 3 just tell you to append a 2, right? Append the first symbol, right? And then we'll see a pair of blanks 3 and 4, and then you'll just append the 3. So on and so forth until we get to this position 4 or 5, and this is this blank P, right? A reminder, when you see this blank P, then you append a P. I won't do this in the same detail all the time, but then we append 4P, okay? And then we see here a P blank, and then we append a blank. Okay, so you might notice by the time we get to this state, it looks like the first state, but we've rotated memory and we've put the position controller one step to the left. Okay, and then if we just continue till here, you can see that now we've realigned the queue to have the same data 1 to 6, but we've just shuffled the position controller one step left. And so this block from the start to here would be enough to implement, kind of one cycle of a Turing machine that moves the memory head, the read-write head one step left. Okay, and then you can see this just continues the run. If you keep continuing the run forever, you'll notice it's ultimately periodic. So if you keep running this, I truncated it too early. If you keep running this, you should eventually see that the position control will wind up right back in this position. So it's just a periodic system, just moving the P marker cyclically through the list. Okay. Okay, first construction. Second construction is that it turns out that basically what we can do is pass messages in a counterclockwise order around the list with the legs. Okay, so what we're going to do is we're going to simulate a Turing machine by a bunch of message patterns. Now, there's two things we need to do. We're going to need to be able to pass messages around, but we're also going to need to be able to remember a position. And so I'm going to skip ahead. So it starts to look a little bit more elaborate, but here's the rule system, rule system 7, where rule system 7, all it does is it passes a message counterclockwise around the list, but it also uses these two other symbols, W and T, to stay stationary at the first point. So we can pass a message while still remembering where we started. Okay? Why would you care about that? Because we can easily move control counterclockwise, but if we want to move control clockwise, the mechanism is going to be remember where you started, pass a message around, and detect when the message has landed one step to the right of where you started. And then trap that message and then update everything one step to the right. So this is going to be a sequence of like ever more kind of intricate like message passing systems. So I won't walk you through all of these, but basically the construction just shows progressively how you can simulate like more and more elaborate leg systems that capture more and more elaborate behaviors. I think I want to show you this one. So I'll just run the system and you have to trust me the definition. So here's the same kind of system where we start with a position controller in position 5. So we start in position 5. We want to send a message back to position 4, but we don't want to forget we started in position 5. So what you'll notice about this system here is that we definitely move the message P around in a counterclockwise order, but we always remember where we started. So a W or a T always stays associated with position 5. Okay, so that means we can both like send messages and remember our position. Okay, just the final demonstration. So this is all written and proved correct in the paper, but it's basically last demonstration. So that rotates memory one position to the rotates the position one step to the right. Okay, and it's pretty elaborate. I wouldn't expect you to sort of read or appreciate it, but I can definitely run this here. Okay, so it takes longer, but here's a demonstration. So here's a demonstration of a leg system where we start out with a position control marker in position 5. And what we want to do is move the position control one step to the right, to position 6. If you run this system, it's not a big memory, but it turns out it's a cubic time process. If you run the system, what you'll find is eventually it produces a memory string where you've moved the marker one step to the right. That is, we started out with a position control in position 5, and we've now moved it to position 6. Okay, so you can implement one step to the left or one step to the left. Once you can implement one step left or one step right, it's really easy to simulate a Turing machine. Okay, so finally, let me show you a Turing machine simulation. But basically, that's what this paper does. Is it first shows you how you can simulate the position control, proves that the position control is correct, and then shows how we can use position control to simulate a Turing machine. So here's, just simulating a Turing machine with a finite memory. I'll come back to that in a minute. Okay, so next step is to simulate a Turing machine with a leg system where we're going to simulate it by doing a bunch of message passing position control locations to move the read-write head left or right, depending on the Turing machine state. Now, the additional thing we need to do instead of just moving the read-write head and writing memory, is we need to keep track of the state of the Turing machine. Okay, so for the Turing machine simulation, here, let me just skip to this one moment, is that I'm going to use this construction for a symbol in the leg system. Each symbol in the leg system is now going to be a triple. We're going to remember the data in the Turing machine memory in the first symbol. We're going to remember the state of the Turing machine in the second symbol, or blank, and I'll come back to that later. And then we're going to use the third position as a position control, like to keep track of where's the read-write. Okay. And so that's just writing the same thing in a bunch of pure formalism. Let me show you the construction. So on the screen, literally, is a set of rules where you give me a Turing machine defined by a finite set of symbols, the finite set of states, the finite set of symbols, the blank symbol, the initial state, the halt symbol, and the transition function. You could literally compile it, and this is the compiler. You literally map it into this finite set of rules, which are rules for the leg system. Okay, and notice that the rules operate on pairs of symbols. They look at a pair of symbols. Each symbol is a triple, which is the content of the Turing machine memory, and then the second triple is a blank or the Turing machine state, and the third symbol is a position control. Okay, and so we have a bunch of, like these rules, for example, just rotate memory, right? We dequeue the first symbol and we enqueue the same symbol to the end. Now, notice that we keep most of the second symbol blank. So the way the simulation is going to work is that the second position is going to be blank, except in one location. And the one location is going to keep the state of the Turing machine, and it's also, the location is going to denote the location of the read-write head of the Turing machine. Okay, and then the third position is going to do all of this message passing stuff. Okay, so anyway, for a given Turing machine, there's this finite set of rules you create, and then you can basically run the leg system on the set of rules. And then the claim is that the behavior of the leg system on this set of rules exactly simulates the step-by-step execution of the Turing machine on its memory for any initialization of the Turing machine. And the simulation will stay equivalent to the Turing machine simulation forever. Okay. So let me just sort of briefly show you the claim, and then I'll show you a couple demos, and then I won't be able to convince you of the proof, but at least I'll show you how it works. Okay, so here's the theorem statement. Tragically, the theorem statement occurs at a page break with a footnote in the middle. So this is terrible for them. But the theorem statement is okay, got a few elements. So the theorem statement goes as follows. You give me any Turing machine, which has a finite description, right? You give me the finite set of states, the symbols, the blank, the initial state, the halt set, and the transition function, all finitely described. Okay, and you give me an initial memory configuration. You give me the state of the Turing machine memory. Okay, and you give me a start location of the Turing machine. That is, you tell me where the read-write head is located. Okay, and it turns out this is legal fine print. It works best if the memory is size 3. And anyway, just ignore the fine print, but all those special cases are handled. So basically, you give me a Turing machine, memory contents for the Turing machine, initial position for the read-write. Okay? Then the claim is going to be that we can generate from that Turing machine description T a set of rules, okay, which I just showed you. So we get a finite set of rules for the leg system corresponding to that Turing machine. And given the memory of that Turing machine, I can construct an initial string for the leg system, right? Where the read-write location, is marked in that initial string for the leg system corresponding to the read-write location of the machine in the initial state, okay? Then the proof is a proof by induction. If we initialize the leg system, right, using those rules with the memory, so here is the corresponding initial memory for the leg system that corresponds to the configuration of the Turing machine, then the proof goes by induction. It's going to say for every single operation of the Turing machine on its memory, the leg system operating with the corresponding leg system memory is going to undergo some finite number of computational steps to end up with another leg system memory that will correspond to the next Turing machine configuration. Okay, so for every Turing machine configuration, given an equivalent leg system memory, the leg system is going to eventually land up in another memory that exactly corresponds to the next Turing machine configuration. And we will show this case by case for every state of the, for every update of the Turing machine, there will be an update to the leg system memory eventually that is exactly equivalent, okay? And the proof is by cases, and there's just 3 cases. The cases are the Turing machine moves the read-write head 1 step to the left. The other 2 cases are when the Turing machine moves the read-write head 1 step to the right, but doesn't go past the delimiter, or it goes 1 step to the right and it hits the delimiter. Okay. Now, the thing about this proof is just this proof by induction. You just establish these 3 cases. The thing to realize is that 1 clock cycle for the Turing machine, 1 step for the Turing machine, is not 1 step for the leg system. So for 1 step of the Turing machine, the leg system runs a long time. Okay, but the leg system runs a long time, but it ends up with a memory string that matches the next Turing machine configuration. Or put another way, the leg system simulates the Turing machine, but the leg system has a polynomial time overhead. So each constant step in the Turing machine is a cubic time simulation in the leg system. So the leg system simulates the Turing machine with a cubic time overhead. Okay, so it's a little bit hairy, but anyway, the proof works. And you can show an exact side-by-side simulation of any Turing machine on any input with a fixed leg system operating on a particular memory string derived from the initial configuration of the Turing machine. And the simulation will work forever on any input string for the Turing machine. Okay, this is most of the paper. So essentially, most of the paper is showing essentially a compilation procedure of a Turing machine to a leg system and a proof that the leg system can exactly implement or simulate the execution of that arbitrary Turing machine on an arbitrary input to that Turing machine. Okay, that's most of the work. After that, everything gets simple, but I might as well show you. Here's one of the simulations. So there is a Turing machine. I think this Turing machine I just showed you here. This is a Turing machine that recognizes strings of a run of 0s and a run of 1s and a run of 2s of the same length. Here's a bunch of runs of that Turing machine on different strings, and it's accepting or rejecting strings depending on whether or not they match the pattern. And we can run now a leg system simulation of this Turing machine. And full disclosure, all I did is I literally took that Turing machine and run the compiler to generate the leg system rules and then just run the leg system. Okay. Now, because of the cubic time overhead, I have to show you a very small example because the runs are quite long. But for example, if we look at this, here's an example of the Turing machine running on an input string consisting of a 0 and a 1 and a 2, and it turns out the Turing machine accepts that string, okay? And the Turing machine takes 7 steps to accept that string, okay? So we can run the leg system simulation of that Turing machine, and that's what this last demo will do here. It's this one. Okay, where are we? Oh, I have to come back in here. Useful to read. Okay, include So this will first compile, like it first runs the compiler from the Turing machine description. It generates the rule set for the leg system. And then it runs the leg system on all these instances, and it's going to spew off. Okay, so now it's compiling, and then it's going to start running these leg system simulations. It shouldn't take too long. Here we are. Okay, so it turns out the Turing machine had 5 states, or maybe it was 6 states, but the leg system has 242 symbols and 4,676 rules. Okay, anyway, so this shows, okay, actually this is too trivial. Let's go to a better example. So this is running the leg system on increasingly interesting examples. Let's go to this example here. So the execution is pretty fast. Okay, so here is the same, remember the Turing machine, we ran the Turing machine on the string 0, 1, 2 delimiter. And the Turing machine accepted this string. So here we have the corresponding memory for the leg system, initialized where the Q naught, the initial state of the Turing machine, is indicates that the read-write head is in position 0. Okay, and then we were going to run the leg system simulation. The Turing machine stopped in 7 steps. The leg system stops in 263 steps because it's doing all this message passing around the memory queue. Okay, but you can see that it ended in the same state Q5. It ended with the Q5 on the new blank symbol that got generated. You can see that the memory is expanded by 1 step because the Turing machine expanded memory by 1 step. And it has exactly the same markers, like a marker Y where the 0 was, a marker X where the 1 was, and a marker X where the 1 was. Anyway, you can go back through this long sequence, and you can see here's the the initial configuration that corresponds to the Turing machine initial configuration. And then if you go far enough along here, we can find the next configuration. I think it would be, let's see here. So we start in R, it'll be where we see a little r. So it might be a bit hard to find. There's going to be a position, I think, here. So I think the first step of the Turing machine was 44 steps of the leg system. Something like that. Anyway, on and on and on it goes. Okay. All right, back to the paper. Let me finish this off. Oh, is this the end of the class time?
8 minutes.
We can go until 5 o'clock.
Okay, 8 minutes. No, that's good. I can do this in 8 minutes. So, okay, so essentially, what have we done? I introduced leg systems. I showed you stuff about leg systems. And then basically, I proved to you that a leg system, for every Turing machine, there's a corresponding leg system that exactly simulates, is able to exactly simulate the execution of that Turing machine on any input to that Turing machine. Okay? What I haven't shown you is anything about language models. Okay, so then, so I have to go back to the language model thing, and this doesn't take long. By the way, we could show a couple of things, like any linear bounded automaton. So a linear bounded automaton is a Turing machine that never expands memory. And so we can show that we can exactly simulate any linear bounded automaton with a leg system that never expands memory, which means the leg system only ever looks at two symbols and only ever appends one symbol. So that's powerful enough to simulate any linear bounded automaton. Okay? But linear bounded automaton, because they cannot grow memory, are not as powerful as Turing machines. Skip this. Okay, now the thing we care about is a universal, like, so we basically have a general compiler that can compile any Turing machine into a corresponding leg system. The next step in the proof is to take a proved universal Turing machine and compile that, okay? So, we take this universal Turing machine U15 true. So believe it or not, this is a Turing machine with 15 states. This is the Turing machine right here in table 1. This Turing machine has been proved to be a universal machine. This Turing machine can simulate the execution of any other Turing machine on any input. And this is proved not by us, this is proved by Nereid Woods back in 2009. And this is just not the only, this is one of the smallest known proved universal Turing machines. And since the 60s, there's been tons of people trying to prove different smaller Turing machines universal. So we just take this universal Turing machine, I run it through the compiler. I have that, I can show you the demo, but it's not going to show you. I run that machine through the compiler, and we get a set of, where is it? We get a set of 1,857 rules. Here it is. 1,857 rules on 249 symbols. And of the 1,857 rules, we only have 14 rules that generate 2 symbols. All the other rules generate 1. So most of the leg system just rotates memory, doesn't grow memory. The 14 rules only correspond to the special case when the Turing machine read-write head hits the delimiter and we need to insert a new blank symbol. So there's a couple of rules that handle a blank insertion. Okay. All right. And so that's just running the compiler. The correctness proof is the correctness proof of the compiler. By a simple consequence, show that the rule system for this particular Turing machine is still correct. Okay, so then the final proof that this is a pretty old one now, we did this a few years ago, but essentially how we took a language model and used it to simulate a Turing machine is as follows, and its brute force is we literally took, at the time, Gemini 1.5 Pro, this is like a year and a half ago, and we took the entire set of rules, 1,857 rules, and we just gave it as a big system prompt to the language model. And actually, we did some prompt tuning. It turns out language models are really good at Python. So we didn't give rules to the language model. What we said is, imagine you get a big Python dictionary. And the dictionary is, the key is the pattern, and the value is the next symbol that you want to append. So we just, as a system prompt, give it a big Python dictionary explicitly, okay? And then the way the thing operates is that we then give the language model the context of the Python dictionary and then a single key, okay? And we ask, here's a dictionary, and then, for the key blah, what is the value? And then that's the prompt to the language model, and then the language model is supposed to respond with the correct value, okay? And then we just check in this first scenario, we verify that we can get the zero temperature decoding, like, a fixed random number seed language model to give exactly the correct response for each one of the 1,857 contexts. Now, full disclosure, Gemini 1.5 Pro is a pretty good model. The reason we used it is not because we were working at Google at the time. The reason we used it is that the system prompt was 42,000 tokens. And at that point in time, the language models were only up to 16,000 to 32,000 tokens. the system prompt, the rule set was too big for the llama models to use. It was too big for the other models. So we had to use Gemini 1.5 Pro because that one had a 1 million size, 1 million token context. So it just had a big enough context window that we could fit the dictionary. Now, it turns out if you just give the dictionary, it still made mistakes. So actually what Hanjun did back then is we copied the dictionary. So we essentially had 2 copies of the dictionary, one in one direction with 2 different orders, and then a couple of other patches as the system prompt. But we're eventually able to get that one system prompt to successfully pass each case, okay? The way this would operate, though, is shown in this image, is that you keep the same system prompt, but you just append the next size 2 context window, roughly saying, here's the system, here's the dictionary, given the key blah, the next value is. And that generates the next value, and then we construct the next prompt, and this runs a cycle that simulates any Turing machine. Okay? And that's the story. Now, I realize we're at time. We can maybe debate offline about what's pleasing or not about this construction. But one last thing, I should not do the Hall of Mirrors thing. One last thing to say is that Alex Lewandowski has since been able to reconstruct, been able to reconstruct this proof for random language models. So it turns out that big language model only need to memorize like this small set of rules. And so Alex was able to show that you can get this proof to work for pretty small random models. So it doesn't really need the full power of the language model. Even the random initialized model would work. Okay, I stopped there. Sorry, I'm at time. I can hang around a few minutes if people have questions, but it was a slightly awkward setup. Sorry.
I had a quick question.
Yeah.
In the example you showed where you have to put the whole instructions in the context.
Yeah.
When you use it, does it have to keep that system prompt within its context, or what happens?
Absolutely. Absolutely. So this is the problem, right? Like if you run so say you have like a 2 million context window, but everything has to fit in context, that cannot work. This kind of goes back to the start, right? Is eventually the computation or even the input to the model is bigger than the context window, right? And the context, so the system prompt has to be in context.
No, I understand that.
The response to the current sort of key or the current sort of active working memory pair.
Right, but after that, as it keeps generating, does it have to keep the system prompt like inside context and keep looping it or something?
No. So again, the way you think of it is the memory string is we have to keep track of the memory string outside of the language model because the memory string is potentially arbitrarily large.
Yeah. So
we just keep track of the memory string. We know where the current context window is in that memory string, right? And we've appended all the generated symbols to the end of that memory string. But any point in time, we know what the current context window is, size 2 context, right? And we know what the memory string is. And then we just construct a prompt for the language model, which is system prompt appended with memory string, current context. And that's the active context for the model. So the model only ever has to respond, basically the model only responds in the first scenario where it's system prompt plus current context. And it's an external, externally where that current context is tracked. The language model doesn't track the current context.
Oh, I see. So it would, so from the actual external tape, it's passing in those S1 to SNs.
It's keeping track of where it is. Yeah.
Yeah. I see.
Yeah.
So the way to simulate the Turing machine is you always have the system prompt and then you always append it with the current string from the part that's working.
Yes, Vlad, and I didn't mean to cut you off, but full disclosure, and look, I'm not revealing any super secret Google things here, so don't call me on that. But every language model you interact with has a big, massive hidden system prompt you never see. All language models, publicly available have this.
Yeah.
It's not a Python dictionary, but there's a big system prompt behind the scenes, right? I mean, that's the way they function. So, and that's always first, right? So there's always some hidden, so the actual prompt that goes into the actual model is constructed from what you ask, but a bunch of other stuff is going on in behind to construct that prompt.
Yeah.
So it's kind of a version of that.
I have another question. So
Yeah.
here, you constructed this set of symbols, etc., to sort of model this Turing machine and the position codes and all that. And you're putting all that in the system. And then when you talked about making a random model, so then you need to figure out which symbols in that random model are going to do what you want from them, right? So how do you figure that out so that you can figure out how to program the random model?
Yeah, you know what? I should pull up my talk slides. I'm sorry, I didn't have them up, but that's exactly what Alex did. So he basically, he implemented an encoder and a decoder neural net outside of the language model, where the encoder and the decoder only map symbols to, symbols to quote symbols for the random model. And then all you have to do is train the encoder decoder. Like there's a few technicalities, but you train the encoder decoder so that each one of the 1,857 behaviors is exactly correct. So you take the rules as we wrote them in the proof here. That's a pair of symbols. The encoder takes the pair of symbols, maps it into a pair of something. Well, maps each symbol, sorry. The encoder maps symbols to symbols, right? So it takes the pair of symbols and then two applications of the encoder, maps it to a new pair. That new pair is fed to the random model. The random model emits one or two symbols, but we'll take like the pair. Actually, we take a triplet of the output symbols generated by the model. And then the decoder takes each one of those output symbols and learns a symbol, inverse mapping, a symbol to symbol mapping back. And then the encoder and decoder are just trained to try to make sure each one of these 1,857 cases passes. And it turns out this is pretty easy. It works pretty well. Pretty small random models, you can train them pretty quickly to start work. So essentially, the way the machine works is there is a set of inputs to the random machine. Like there's basically, it was 249 symbols. There are 249 inputs to the machine that if you construct input sequences from those 249 symbols, feed them through the machine in this, with context window size 2, the machine will emit symbols that actually wind up being, that can be mapped back to a canonical, symbol in that set of 249 that exactly simulates the execution. Can I say, I forgot to say one other important thing about this proof, which is, I was tipped off that you guys have studied Will Merrill's work, which is amazing. Will is awesome. Like Will is one of the coolest people in this field I've ever spoken to. But one difference between this kind of proof and the other kinds of proof is there's a lot of proofs going way back to the 80s showing that like various RNNs are Turing complete, but all of those proofs are of two types. They're existence proofs in terms of representability, or maybe they're existence proofs that'll say something about learnability. But what those proofs do not show is if you give me a real model, a real frozen model, they don't say anything about that particular model. And the difference is this proof tells us something about a specific model. So for example, Alex has gone out and proved like Llama 4, 17B, as it exists, is already a universal computer. Like it's not a hypothetical property. It's a real proved property of the live model as it exists. And to me, even though these proofs are really rather simplistic compared to the much more sophisticated circuit complexity stuff going on out there, and even more sophisticated learnability stuff going on out there, I think that stuff is all awesome. But they are not able to talk about the properties of a particular instantiation. And I think that this is important, is to be able to say the models right now are already general purpose computers, just like your laptop right now is a general purpose computer, if we overlook the fact that you have a finite RAM and finite secondary storage. So I feel like this is kind of an important factor that people often overlook. Maybe we should let people escape.
I'm gonna stop recording.
Yeah.